Hello everyone, I am Sanjeev and I welcome all of you to Searching AI, and this is the third presentation in the course ARL 1011. So the topic for today's presentation is the geometry interpretation of Bellman residual minimization and fixed point methods. In this presentation, I will discuss about the Bellman residual minimization and the fixed point solution for solving various problems in reinforcement learning. So let's begin with the Markov decision process. So an MDP is a 5-tuple defined by S, A, P, R, gamma, where S is a set of all states or the state space, A is a set of all actions that the agent can take in any given state. P is a Markovian transition model or the transition probability whose components P, S, A, S prime is defined as PA, SS prime, which is the probability of making a transition to state S prime when agent takes an action A in state S. R is a reward function whose components R, S, A, S prime is defined as R, A, S, S prime. There is a immediate reward received by the agent when it takes the action A in state S and makes a transition to next state S prime. And gamma is the discount factor. So a policy is a mapping from states to actions, where the policy pi gives a probability of taking a particular action A in a particular state S. If the policy is a deterministic policy, then it will assign each action to each possible state. So the target of the control problem is to determine an optimal control policy for a given task. An optimal control policy will give the best possible action such that the reward can be maximized. So for each state, the optimal control policy will give the best possible action that the agent can take in that state. So our target for a control problem is to determine an optimal policy, an optimal control policy for that task. So here's a state action value function. A state action value function defined as q pi s comma a. There's a state action value function for the state action pair s comma a is a expected discounted total reward when agent takes the action A in a state S and makes a transition to next state S prime and thereafter follows the policy pi. And state action pair has to satisfy the Bellman equation for the state action value function, which is given as the where q pi s comma a is r of s comma a plus gamma times sum over all s prime, that is sum over all possible next states, PASS prime, which is the probability of making a transition to state S prime when agent takes the action A in state S, times q pi s prime comma pi s prime, where pi s prime is the action that the agent selects according to the policy pi in state S prime. This pi S prime is the action governed by the policy pi in state S prime. So q pi s comma a, there's a state action value function of state action pair s comma a is r of s comma a. There's a reward function which is given as sum over all s prime PASS prime times RASS prime. There's a immediate next reward multiplied by the probability of making a transition to a next state, which is kind of like the agent takes an action A in a state S and makes a transition to state S prime. Now suppose there are two possible states, S1 prime 1 and S1 prime 2, and S1 prime 1 has a probability of 0.4 and S2 prime has a probability of 0.6. Then this is given as the RAS prime 1 times 0.4 plus RA S1 prime 2 times 0.6, which is given as a expected reward. there's a reward multiplied by its probability. So R S comma A is the expected reward. So arranging these equations in a matrix form will give us Q pi is R plus gamma times P pi times Q pi, where P pi is a stochastic matrix or the transition matrix. Here Q pi and R are the column vector of length mod S times mod A, that is a set of all possible combination of state action pair, and P pi is a stochastic matrix or the transition matrix of dimension mod S times mod A cross mod S times mod A. So P pi represents the transition probability from state action pair S comma A to next state action pair S prime comma pi S prime. That is, if you are in state S, you take a particular action A and then makes a transition to next state S prime, and then according to the policy pi the next action is selected. So the matrix P pi gives a transition probability of making transition from state action pair S comma A to state action pair S prime comma pi S prime, where pi S prime is the action governed by the policy pi in state S prime. So for every MDP there exists an optimal policy pi star which maximizes the expected discounted future rewards for each state, and the target of the control problem is to find this optimal policy. So in this presentation we are not going to discuss how to find the optimal policy like we have discussed in LSP algorithm in the LSP lecture. This lecture focuses on two different methods for solving the problems in reinforcement learning. There is a Bellman residual minimization and the fixed point solution. So to find the control policy pi star, we generally use the policy iteration algorithm, and policy iteration algorithm has two steps. The first step is the value determination, in which the value function, the state action value function for a given policy pi is determined, and the next step is the policy improvement, where the next policy is made greedy with respect to the state action value function of previous policy. So say you have a policy pi t and pi t plus 1. So the value determination step will compute the state action value function for the policy pi t, and the the policy improvement step will make the policy pi t plus 1 greedy with respect to the state action value function of the policy pi t. So in this way, by repeating these two steps, the policy iteration algorithm finds the optimal policy pi star. So here's the review, like value determination step. The value determination step finds the state action value function for the policy pi t, which is denoted as q pi t, and then the policy improvement step makes the policy pi t plus 1 as a greedy policy with respect to the state action value function of policy pi t. So in general, the exact representation of the state action value function in a matrix form is not possible, because if the domain is a continuous domain, then a number of states, there's a mod S, is going to be infinite. So therefore we need some approximation method to approximate the state action value function, and we use the linear function approximation, where the state action value function for a given state action pair S comma A is given as the phi S comma A transpose phi of S comma A transpose W, where phi is a mapping from state action pair to a vector in Rk. So phi and W are a column vector of length k, where phi is a basis function which maps the state action pair to vector in Rk, and this basis function defines a unique vector for each state action pair, and the weight vector W is used for assigning the weight to each of the k basis functions. We have the k basis functions for each state action pair, which are given by the components of this vector phi, and for each basis function we have a particular weight which is decided by the components of this vector W. So in the matrix form, this is given as Q is phi times W. So as I have mentioned that the policy iteration algorithm has two steps, where the number one is the value determination step and the second one is a policy improvement step. So to solve the value determination step, we have two methods. There are more than two methods, but I am going to discuss just two methods because these are the main methods. The first one is a Bellman Residual Minimization, or also known as the BRM, and the second one is known as a fixed point solution, which is known as the FP. The previous algorithm that we have discussed, the LSPI, we have discussed the fixed point solution. So the Bellman Residual Minimization. So here's a Bellman operator T pi, which when applied to a value function results in a one-step transition. So T pi Q pi is R plus gamma times P pi Q pi, and when written in terms of value function approximation, it is equivalent to R plus gamma times P pi times phi times W. And the Bellman residual is defined as the BR is equal to T pi of Q pi minus Q pi. So the difference between the Q pi and the one-step transition, there's a Bellman operator applied to the value function Q pi. The difference between these two is known as the Bellman residual. So BRM, or the Bellman residual minimization algorithm, minimizes the magnitude of the Bellman residual. So it is given as the minimize over the weight vector W, T pi Q pi minus Q pi, and here norm can be any norm, but here in general we choose the L2 norm, the square of the L2 norm. So when written in terms of the value function approximation, it is given as minimize over W, T pi of phi W minus phi W, which is given as R plus gamma times P pi times phi times W minus phi times W. So the Bellman residual minimization solves this minimization problem, this optimization problem, which is also a convex optimization problem, and the result is equivalent to a least square problem. Obviously this is just a least square problem, and therefore the result is simply A times W is equal to B, where A and B are defined as A is phi transpose times I minus gamma times P pi transpose I minus gamma times P pi times phi, and B vector is given as phi transpose I minus gamma times P pi transpose R pi, where I is the identity matrix. So this is the solution for the Bellman residual minimization algorithm. This is obviously the theoretical solution. To solve it practically, we will use the samples to approximate the matrix phi, the reward vector R, and the stochastic transition matrix P pi, because in the real world problem, the exact transition matrix or the transition model and the reward function are not known. Therefore we need to approximate these terms, this P pi and R pi, with the samples. So now comes a fixed point solution. I have already discussed the fixed point solution in the LSPI lecture, and here I am going to describe it again. So the fixed point solution forces the value function Q pi to be a fixed point of the Bellman equation. So the application of the Bellman operator T pi, where T pi, the Bellman operator, is a non-linear operator. The effect of the application of Bellman operator on the value function phi W is that it takes the resulting vector out of the span of the matrix phi, where span of the matrix phi is given by the set of all possible linear combination of the columns of a matrix phi. It is also known as the column span of matrix phi or the span of matrix phi. So the application of the Bellman operator, a non-linear operator, to the value function phi W, which is defined as T pi phi W, the effect is that it takes the value function, the resulting vector, out of the span of the matrix phi, and therefore we project back this vector onto the span of the matrix phi. So pre-multiplication with the projection matrix, which is defined as PR phi. This projection matrix is independent of the policy. So the pre-multiplication of the projection matrix PR phi brings it back to the span of the matrix phi. Therefore, once the resulting vector comes on the span of the matrix phi, then there must exist at least one linear combination of the columns of the matrix phi such that the two terms are equal. So a span of a matrix phi is defined as a set of all possible linear combination of the columns of a matrix phi, and once this vector, this PR phi times t pi of phi of w, this vector lies on the span of the matrix phi. Therefore, there must exist at least one vector w such that phi times w is equal to this vector, and that's what the fixed point solution solves for. The fixed point solution solves this equation, determines the weight vector w, and goes the policy improvement step, and the two process continues until some convergence criterion is satisfied or the maximum iteration allowed in an algorithm are over. So fixed point solution is defined as minimized with respect to the weight vector w, norm of PR phi times t pi of phi of w minus phi of w, where the norm is in general the square-delta norm. So where PR phi is a projection matrix and is defined as phi times phi transpose phi inverse phi transpose. So this is a PR phi, and the pre-multiplication with the TR pi times phi w projects the vector t pi phi w back to the span of the matrix phi. So now let us geometrically analyze the two solutions. There's the Bellman residual minimization and the fixed point solution. So both these solutions result in minimizing the different lengths or the different sides of a triangle. So the three components of the Bellman equation with linear function approximation, the one is a value function itself, which is phi times w. The second is a Bellman operator applied to the value function defined as t pi of phi w, and the third is when it's pre-multiplied with the projection matrix PR phi as a PR phi times t pi of phi of w. These three components form the triangle, and the Bellman residual minimization and the fixed point solution minimizes different sides of this triangle. So suppose this plane or this hyperplane represents the span of the matrix phi, where span is a set of all possible linear combination of the columns of the matrix phi. So the value function phi times w, which is phi times w, there is a linear combination of the columns of the matrix phi defined by the weight vector w. This vector, the resulting vector phi times w, is going to be in the span of this matrix phi, since it is a linear combination of the columns of the matrix phi. So the value function q pi, that is phi times w, will be on this hyperplane or in the span of the matrix phi. And the application of the Bellman operator, which is a non-linear operator, the application of the Bellman operator to value function will take the resulting vector out to the span of the matrix phi. In general, the resulting vector, that is r plus gamma times p phi of phi w, is not in the span of phi. And the projection matrix brings this vector back on the span of the matrix phi. So PR phi, which is defined as phi times phi transpose phi inverse phi transpose, the projection matrix when pre-multiplied with this t pi of q pi brings this vector back on this hyperplane. And once it is on this hyperplane, that is once it is in the span of the matrix phi, then there must exist at least one vector w such that phi times w is equal to PR phi times t pi of phi w. And this is what the fixed point solution is. The fixed point solution finds the weight vector w such that phi w is equal to PR phi times t pi of phi w. Since It is on this hyperplane, therefore phi times w will be equal to this value for some weight vector w. So this is a triangle defined by the three components, the q pi, which is a phi times w, which is in the span of the matrix phi and is a linear combination of the columns of the matrix phi. The PR phi times t pi of phi w, again this is on this hyperplane, and the third component is t pi of q pi, which is in general not in the span of the matrix phi, since the t pi is a non-linear operator. The Bellman operator is a non-linear operator. So these three components defines the triangle, and the Bellman residual minimization and fixed point solution minimizes different lengths of a triangle. So first consider the Bellman residual minimization. So Bellman residual minimization is minimized with respect to w, the norm of t pi phi w, which is this component, t pi q pi, which is t pi phi w minus phi of w. So the norm of the difference of these two components, BRM minimizes the norm of the difference of these two components. That is, BRM tries to minimize this side of a triangle, and the fixed point solution, which is given as PR phi times t pi of phi of w, that is this component minus phi of w, this component. So minimizing the norm of the difference of these two components give the fixed point solution, and minimizing the norm of the difference of these two components gives the Bellman residual minimization. So BRM minimizes the hypotenuse of a triangle, and the fixed point solution minimizes the base of the triangle. So these two different methods minimizes the different sides of a triangle. So I haven't here discussed the bias term that is introduced in the Bellman residual minimization when we use a single next transition state, which is not the topic of this presentation. I will discuss it later when I discuss specifically the Bellman residual minimization algorithm. So this is the overall picture, the geometrical interpretation of the Bellman residual minimization and fixed point solution. They minimize the different lengths of a triangle. Sorry, the different sides of a triangle. So thank you for watching this presentation. I am Sanjeev from searchingai.com.